Good afternoon, this is Schweitzer, and we'll look at a video here involving more on acids and bases. Now, just a recap from the last video, you should remember that, everything that's acidic eventually is going to produce an H+ ion. So, in this situation, come on Ben, give it to me, let's go, come on, there we go, alright. Alright, so every acid, if you put acid in this box, doesn't matter what it is, alright, eventually this acid will output, if it's an acid, H+ ions. The actual acid itself, sometimes called HX, actually isn't even acidic. It has to go through a reaction in order to make it acidic. That reaction itself is what produces the acid from what we think of as being an acid. Alright, so what is this reaction called? It's called hydrolysis. So we're going to look at in this video today is how you make these things chemically. Okay, sometimes it's very simple, sometimes it's a little more complicated, but you'll see here. Okay, so now what is hydrolysis? Alright, so we know water plays an integral role, and it essentially is H+. Okay, let's say HX, our acid. This is a generic acid. And it's going to react with water, and it's going to produce what's called it's going to donate an H to the water. So sometimes an acid is referred to as, like this guy, an H+ donor. Just so you're aware. And we'll see more of this later. A base is called an H+ acceptor. Alright, so what do we get? Now remember, in a chemical reaction, the left-hand side, it really is just a snapshot before, and this is a snapshot after, and there's a little rearrangement that's occurring in between here. So if this guy gives this guy an H+, then what's left? Well, this guy becomes H3O+, and this guy becomes just X negative. And of course, if we stick our finger into this beaker, we're going to, and if let's say it's not too strong of an acid, but we have a little nick on our finger, alright, stick your finger in there, you get yourself a little fingernail here, alright, you're going to feel maybe a little stinging. Is this guy going to sting your finger? Maybe you got a little nick or something, microscopic nick in your finger, and this is stinging your finger. No, it's this guy right here. If you stick a pH meter into this guy, and you're measuring the pH to go into your computer, is it measuring this guy right here? No, it's measuring this guy right here. So this is called hydrolysis. This is the generic form of hydrolysis. Okay. An example of this might look like would be like HCl plus H2O yields, and again we know this is a known acid, so it's going to donate over here, so it's going to get H3O plus Cl minus. So with this term here, it's called a conjugate. What's a conjugate? Well, essentially you should realize that this chloride is the same, it's the same atom, okay, minus the H+. So the same atom on the other side is called a conjugate. Okay, so these two are conjugates. It's like, it almost looks real similar because it is the same atom. Remember, snapshot before, snapshot after, it's the same chemical. It just lost an H. Same thing here. These two guys are the same. It's the same water molecule. It's just added an H+ to it. So these are also called a conjugate. And it could go the other way too, like this guy's conjugate. Let's change the color here for a second. Okay, this guy going this way, this would be the conjugate of that one. So it's like, I'm referring to her as the neighbor on the other side. Looks very similar. Okay, we'll add more about conjugate as we move along through this chapter, but just a heads up, a couple of new ideas here. But the main thing here is right here, this hydrolysis reaction. Okay, all right, let's try it. So let's try a couple on our own. Okay, now we've seen one example, and I even have one that we just did. Okay, but pause the video and try a couple on your own. Alright, so here we go. This is going to be plus water. Yields H3O plus plus Cl minus. And just transferring an H plus over here. So this guy lost an H plus, which is why this positive and negative here. That's really important here that we get those positives and these negatives here. Alright, this guy, plus water, yields H3O plus plus F negative. Alright, this is hydrofluoric acid, this is hydrochloric acid, this is vinegar or acetic acid. And there's no negative here, so I'm just going to go plus H2O yields H3O plus plus C2H3O2 negative. Now, just a little side note for you. Let's remember that in this situation, who's actually acidic? This guy, and this guy, and this guy. Those are the ones that actually do the work. So we'll see later on that these two reactions, the bottom two here, are what we call going to equilibrium. So they're fighting back and forth. And of course, we know in equilibrium that we're never guaranteed to get all the way to products. So that's really a big idea that's coming up in acids and bases, that, okay, we know that since this guy is the actual acid, and if we're in equilibrium, what if we don't make it, what if we have lots of reactant left before when we get to stalemate or equilibrium? So there's a chance that in these acids that we aren't real effective because we just don't ever get that much product. And if we don't ever get that much product, we're never really all that acidic. So this reaction here produces some H2O pluses, so it registers as being acidic. Alright, what is the conjugate of hydrocyanic acid? Okay, let's try another one. Give it a try. Pause the video. What do you think? Two-step process here. One, you got to translate that word into an acid, and then you got to say, what's the conjugate of it? Okay, so HCN. Now this is an acid, and I'm going to let it give an H plus, typically to water, and what's left over? That's going to be its conjugate, CN negative 1. Typical example here also would be to link all the conjugates. So this guy's conjugate is right here, and of course those two. This guy's conjugate is located right here, and of course these two. This guy's conjugate is located right here, and of course these two. Okay. Alright, let's move along. Perchloric acid undergoes hydrolysis, and it goes to completion. Again, that's a little bit of a harbinger of things to come as far as, you know, applying some of the equilibrium ideas we had from the last chapter to this one. But this is going to completion. Write out the hydrolysis reaction. Okay, pause the video, and let's write it out. Okay, perchloric acid, everything starts with an X, an H, and this is going to be perchlorate. So that's ClO4 plus water is going to yield H3O plus the conjugate of perchloric acid, which is ClO4 minus 1. Alright, so let's draw a picture of this. Now again, it's going to completion. So that means it's going to run until it runs out. This is an excess. Lots of water there. So this guy is the limiting reactant. So it's going to run until this guy, initial stoichiometric ratio, and this guy hits a big whopping 0. Okay, it's going to, whatever we have here, it's going to go until it gets to 0. Alright, so in this case, our picture, our model of this thing is modeling a reaction that goes to completion. So it's only going to show these guys. Okay. So depending on how many you draw, it's up to you. H3O plus. And every time I draw one of those, I'm going to draw let's draw 4 of these. There's 3O plus, H3O plus, H3O plus. And then I got to draw, you know, every time I get one of these, I'm also going to get one of these. So I got to draw in ClO4 negative, ClO4 negative, ClO4 negative, and ClO4 negative. Okay. So again, you stick a pH meter in here, or you stick your finger in there. What are you going to sense? What's the meter going to sense? It's going to sense these H plus ions. Okay. How many of them you have here really depends on how many of these you started with. So that's kind of a concentration issue. So high concentrations, low concentrations. Ammonium is an acid that undergoes hydrolysis. Okay, so it's something we've been talking about. This is a real common player in our society biologically. It forms a reactant-favored equilibrium system. Okay, let's get right out the reaction. Let's try it now again. Pause the video, give it a try. What would be the hydrolysis equation for this guy? Pause it, try it. Okay, plus water. And I'm going to allow NH4 plus to donate H plus. Now again, this guy has the ability in nature. We're seeing this happen. This is not something that just because you write it on paper doesn't mean it's real. Okay, so I can't have this guy take an H plus, for example, because that doesn't happen in nature. So we're really using our equations. We're trying to model what's happening in the real world. It doesn't pay to model something that's fictitious. So with that being said, make sure that you understand that we're just modeling what's happening in the real world. So this guy is a known donator of an H plus, and therefore we get H3O plus, and we get NH3, and that is what we left over. Of course, you notice that this guy should look familiar because that's ammonia. Ammonia. Okay, and this guy right here, his name is very similar. Ammonium. Okay. All right. There we go. So, and I would also make one little side note that this is a cation, so there's always going to be an anion associated with it. And the most common way that you would see that is ammonium chloride. That's just so you know, it's just there. Ammonium nitrate. Some anion that happens to be at this point a bit of a spectator. So, what's it going to look like? Now again, this thing is all reactant favored. So that means we're going to go into an equilibrium system where the reactant, it's very heavy in reactant favor. So my K value is equal to a ratio of concentrations of products over concentrations of reactants. And remember that this is just saying that it's very heavily in the reactant side. Okay, so what was my picture going to look like? Well, it turns out that it's very reactant favored. So we're going to draw a lot of the reactants and very few products, if any. In fact, it's so reactant favored that they might draw it like this, okay? NH4 plus. Now the whole thing is water, so I'm not going to draw any water molecules. NH4 plus, NH4 plus, NH4 plus, NH4 plus. Now, in a real world, if you were to measure this thing, about, on average, about 2 to 5% actually makes it over at stalemate. So that would mean that we would need to draw 100 of these guys. If you want to draw it proportional, you would need to draw 100 of these, and then you could draw 5 of them out at the high end. Maybe only 2. So you could draw 5 of these, you could draw 100 of these, and then you could draw 2 to 5 of these. 2 to 5 of these. That's what that means. It's a ratio out of 100. So with that being said, scientists and people who do this stuff tend to just leave it like this and say, okay, we're not going to show any product because it's just really, really small, but this stuff is nasty. This stuff is really nasty. And you definitely, when I was a kid, we had these little Mr. Yuck stickers that they'd put on stuff underneath the counter that you're not supposed to eat. But anyways, that being said, it's really nasty. So even if I drew it like this, it's assumed that this thing is still going to be acidic because even the really small amounts of this stuff is measurable and is definitely noticeable. But that being said, if you want to draw some products, okay. But you certainly, if you want to try and keep your proportions as best as possible, you're only going to draw one of them. You don't want to draw a bunch, okay? Again, yes, so that's how I would show it. On a college level or an AP level, they wouldn't show any. They would just show this, and they wouldn't show this because they wouldn't want to be that far out of real life. They'd rather draw 0 than draw all of them. But this is nothing wrong with this either. Just don't draw more than 1. All right, and that is good. Alright, so let's take a quick moment, pause the video, and write out some hydrolysis reactions for these various acids. Okay. Alright, give it a try, pause it, and then we're back. So this guy's going to be HF plus H2O yields H3O plus F negative. HCN plus H3O plus CN negative plus H3O plus. And notice I wrote it out of order. You know, the beaker doesn't care which way you put it on the paper. So I want to put a little forward sign there. Okay, acetic acid is HC2H3O2 yields. Let's erase that for a quick second. I'm going to put a plus there. Plus H2O yields H3O plus C2H3O2 negative. So look, it's kind of similar here, right? We've done some of these already, even, but if you try some of these, you'll see they're just starting to get easier and easier, and you'll find that this is really just following that little template. Hydrobromic acid, okay, HBr plus H3H2O yields H3O plus Br negative. Alright, and then let's go nitric acid, okay, good practice for translating some names here. Plus H2O yields H3O plus NO3 minus. And then sulfuric acid, now this is a little bit, maybe a little trickier one. Okay, let's see how we do this. H2SO4, okay, plus water, H2O. And depending on the situation, it can give one H or it can give two H's, but water can only take one of them. So I'm supposed to do one first. Would be H2O, all right, H3O plus, and then plus HSO4 minus 1. That's the most common reaction. If we keep allowing it to donate, then it's going to be the next one. There's a little more to that as I'm just kind of hitting around some ideas. That would be plus water yields SO4 minus 2 plus H3O plus. Alright, good. Let's move along here. Alright, what's a conjugate? What's the acid-base conjugate pair? Okay, so this is reviewing some of the stuff we talked about earlier. So a conjugate is basically the same atom, you know, on the other side of the reaction with just minus an H plus ion. So it's a substance, okay, either plus or minus an H plus ion. Okay, an acid-base conjugate pair are the ones we're linking. So it's the same. It's the same substance. The pair would be the reactant version and the product version. And we'll see some of those. So let's write out the hydrolysis equation for these acids and bases. And now we're going to start letting you, I'm indicating that's acid and base. We're just doing a little more work on your own here. Alright, so this is an acid. So to pause the video, I would like you to write out the hydrolysis equation, and then I want you to link them for acid-base conjugate pairs. Now, one thing, I'll talk a little more about the acid-base version of this as we get to the end, but try it on your own first. Alright, back, plus water yields NH3 plus, okay, it's acid, it's going to donate, so that's what's left over, plus H3O plus. Alright, I'm going to do all the reactions first, and then I'll link them as we come back. This guy just is now a base. Well, let's run this one through. Plus water yields NH4 plus OH negative. Now that's a new one for us. I'm going to let the water donate back this way. Okay, so we have yet to see that version here, but that's a new idea here. All right. CN, it's a base, so it's going to accept an H+. So plus water, H2O, yields okay, plus water, H2O. So it's going to donate back this way. We're going to get, therefore, HCN. Now it's plus, so now it's back to neutral, plus OH negative. So, interesting note here. Now, how would we go about linking these things? Okay, well, they're really easy to link because they look just like each other. Those two are conjugates. These two are conjugates. Okay, and then here, these two are conjugates. These two are conjugates, and these two are conjugates. Okay. Now, what about this acid-base pair idea? Well, it turns out that, sometimes I use a basketball. In class, I might say, okay, if I have a basketball, I would be considered the ability to give away an H, or the ball. So an acid is often thought as an H plus donor. It can give away the H plus. So if I take this ball and I give it away to somebody else, okay, now before I was an acid because I have the ball. But once I give the ball to somebody else, then in this situation, now they have the ball and I don't. So this is the after picture. Again, remember, a chemical reaction is just a before snapshot and an after snapshot. So now this guy's got the ball, and I could put a heme inside this, say I have the ball and this guy doesn't have the ball. And now I don't have the ball, but now this guy does. Okay, which is fine. Am I still an acid? And the answer is no, because I don't have a ball to give away. So the ball is the H plus ion. And you should note at this point that the acceptor, the person who wants the ball, is the base. So now, not only am I not an acid, I now technically have a void here where I could take up H plus. Therefore, I am now a base. So as the reaction proceeds, an acid starts out as an acid, but then becomes what we call the conjugate base. And notice that this is basic. This is now the base because it's the acceptor. This is the, this one, I put that in the wrong one. This one goes to that guy. This is the conjugate acid. Alright, and this guy is my base, as marked here. This is my base. This is my conjugate acid. This is my acid because it's donating. This is my conjugate base. This is my base. This is my conjugate acid. This is my acid. This is my conjugate base. Okay. Now, again, a lot of that's just some theoretical stuff, and we'll see a little bit more how that works and how it's used, but that's the basic idea. Alright, so this video just talks a little bit about the hydrolysis equation, which is going to be HX plus H2O yields H3O plus X negative. Now, this is the acid version. So we notice that this guy is giving to the water, but we just at the very end tiptoed our way into the basic version, and we'll talk more about that in the future, which is going to be just the opposite, where we have something plus water, okay, and I'm going to back up a second here. Well, it doesn't make a difference, but I'm going to call it X negative, let's say, plus water, and this guy is going to allow this guy to get from water. So this is our two versions of this guy. This gives me HX, I'm going to be back my acid, and then plus OH negative. So that was in there just a little bit. Thank you.